I Neha Yadav, Assistant Professor in ABES Engineering College, Ghaziabad. Today I am going to teach the fifth topic of Unit 4 of Discrete Structure and Theory of Logic. The topic is Subgroup, Cosets and Lagrange Theorem. What is a subgroup? A non-empty subset H of a group G star is subgroup of G if H star is a group. So what is a subgroup? If there is a group G with any operation star, then we can have a subgroup of this group, let it be H and star. So this H should be the set which is subset of G, and this operator should be the same operator. If there is the operation in the group is addition, then the operation in the subgroup should also be addition. So the operations are same, and this set is subset of the set in the group. And as we know, group satisfies all the properties of group, which is closure, associative, identity, and inverse. It satisfies these four properties, that's why it is a group. So the third condition for a subgroup to be a subgroup of particular group, the subgroup should also be a group, or subgroup should also satisfy all the four conditions of the group, which are closure, associative, identity, and inverse. So the properties are: the set should be subset, operator same, and it should also satisfy the properties of group. If this is the case, then H will be the subgroup of group G. Here the example is given. The multiplicative group 1 minus 1 is a subgroup of multiplicative group 1 minus 1i. Here the example is elaborated. For example, here the set is given this. So here the H is given as this. The set is 1 minus 1, and both are multiplicative operators. So the operations in H is multiplication, and the G is simply a group. We know that 1 minus 1 I minus I is a group. We checked for the properties of group here in the previous lectures. So now we will check whether this is a subgroup of G or not. In the question, in this example, it is already given that this is the subgroup of this. So it is, we can see that this is the subset of this. So the first property satisfied, this operator is same as this. So second property satisfied. The third property 1 minus 1, this set with multiplication operator satisfies all the properties of group or not. So we will check for the first property. For algebraic structure, it should follow the closure property. So for closure, to check for closure property of finite group, we have to make the closure table. Here the operation is multiplication. So 1 into 1 is 1. 1 into minus 1 is minus 1. Minus 1 into 1 is minus 1. 1 into minus 1 into minus 1 is 1. So we can say that closure property is satisfied. We can check for associative property, as there are two operands only. So associative property will automatically satisfy. Now I will check for identity elements. For multiplication, we know that identity element is 1 and 1 is here in the set. So identity element also exists. Now we will check for inverse. So identity is 1, so inverse of 1 is 1. Inverse of minus 1 is minus 1. Inverse of minus 1 is minus 1. So inverse of both the element exists. So here this is subgroup of G, as it satisfied all the properties of group. So H is the subgroup of G. Next topic is coset. What is a coset? If H is a subgroup of G star and A belongs to G, then the set HA. So the operation here will be the operation which is given in the group. HA is called the right coset of H in G, and AH will be known as left coset of H in G. For example, H and H plus 1 are two cosets of subgroup H is equal to 2Z. So So I will elaborate this example. Here the group given is Z plus. We know that Z plus is a group. It satisfies all the four properties of group. The properties are closure, associative, identity, and inverse. All these properties are satisfied by this group. So this is a group. It is already given in the question. The subgroup here is 2Z. It will be 2Z. We can expand the set. If we can expand the set of integer, the H will be 2Z. So it can be, for example, this Z is, we can write Z as -3, -2, -1, 0, 1, 2, 3 till infinity. This is Z. Then what will be the H? H is given as 2Z. So H can be written as -6, -4, -2, 0, 1, 4, 6. This is H. This is Z, this is H. Now we have to find the coset for this subgroup. The way to find the coset for this subgroup is we have to perform the operation. We have to perform the operation with an element of that particular group. The group is Z. So we have to perform operation with any integer. So, and the operation should be the operation given in the group. So here the operation is plus. So we have to perform, we can do anything. Plus is commutative, so we can find the left coset or the right coset. So I will just take a simple integer 0. Let it be 0. So here it will be same as H. -6, -4, -2, 0, 1, 4, 6. It will be H. Now I will find another coset H plus 1. It will be -5, -3, -1, 1. This will be, here it is -5. This is -4. This is -1. This is here. This is 2. So it is written wrong. So this is 2. So this will be 3. And this will be 5. This will be 7. So this is this. So H is this. H plus 1 is this. Now H plus 2. H plus 2 will be, we add 2 to H. So if we add 2 to it, I will get -4, -2, 0, 2, 4, again 6, blah, blah. So if we find H plus 3, we will again get set of odd integers. So we are getting repeated values. This is the set of even integer. This is the set of odd integer. This is again set of even integer. This is again set of odd integer. If we can conclude, we are getting only two distinct cosets, which is H and H plus 1. So for this subgroup H is equal to 2Z, we have only two cosets, which are H and H plus 1. So here in example it is given that H and H plus 1 are two cosets of subgroup H is equal to 2Z in the group Z plus. Consider another example. Find all the cosets of 3Z in the group Z plus. So this question is similar to the previous question. Here the set in the group is same as we have seen previously. It is set of integers, so we can say -3, -2, -1, 0, 1, 2, 3, 4. This is the set in the group is given. Here the subgroup is 3Z, so H is equal to, it is 3Z. So it will be -3, -6, -3, sorry, 3 is -9, -6, -3, 0, 3, 6, 9, 12. Now we have to find the coset. So H plus 0 will be H only. Now I have to find another coset H plus 1. H plus 1 will be -8, -5, -2, 1, 4, 7, 10, 13. H plus 2 will be -7, -4, -1, 2, 5, 8, 11, 10. H plus 3. Now we will check. Here it is not repeating. We will find the coset till we get a repeated set. So H plus 3 will be minus 9 plus 3 will be minus 6, minus 3, 0, 3, 6, 3, 6, 9, 12, 15. So here I can see that I am getting repeated values. H plus 3 is same as H. So I will stop here and I will take all the distinct sets as my cosets. So coset for 3Z are H, H plus 1, H plus 2. These are three cosets for the subgroup 3Z. From these two examples, we can also infer that, and we can also conclude that for a coset which is nz and for a subgroup nz, if group is z addition, we can say that we will get the coset as h plus 1 till h plus n minus 1. So this is the conclude. Now here is another example. Here the subgroup given is H having two elements 0 and 4, and the group is having which is Z8. Z8 means 0, 1, 2, 3, 4, 5, 6, 7, and the operation is addition modulo 8. So here we have to find the cosets. So the process is same. We will perform addition operation, addition modulo 8 operation with 0, then with 1, then with 2, then with 3, then with 4. So H plus addition modulo 8, 0. It will be 0 addition modulo 8, 0. 4 addition modulo 8, 0. It will give us 0 and 4. Now H addition modulo 8, 1, the second element. So here we will just perform addition modulo 8 with 1. So here we will get 1 and 5. Now H addition modulo 8, 2. We will continue doing this till we will get a repeated set. So 0 addition modulo 8, 2. 4 addition modulo 8, 2. So I will get answer is 2 and 6. Now H addition modulo 8, 3. So 0 addition modulo 8, 3. 4 addition modulo 8, 3. So here I will get 3 and here 4 plus 3 is 7 and divided by 3, 7. Now it is H addition modulo 8, 4. 0 addition modulo 8, 4. 4 addition modulo 8, 4. So I will get here as 4 and here 0. So here I can see that this is equal to H. These two sets are equal, containing two elements 0 and 4. We will check for, we need not to check further, but I will just check for one more value. 0 addition modulo 8, 5. 4 addition modulo 8, 5. So this will give us 5 and 1. So this is again H plus 1. So here it is repeating. From here the values are repeating. So for this particular subgroup H, the cosets are H, H plus 1, H plus 2. The plus is not exactly plus, it is the operation given in the group. H addition modulo 8, 3 and H addition modulo 8, 4. These are the, sorry, not 4, only these 4. H addition modulo 8, 1, H addition modulo 8, 2, H addition modulo 8, 3. These are the 4 cosets for this particular subgroup. So from here I can make a conclusion that if we take the union of any 4 cosets, if we take union of any 4 coset, for example, this is if we take union of H union H addition modulo 8 1 union H addition modulo 8 H addition modulo 8 2 union H addition modulo 8 3. If we take union of these sets like 0 this and this, we will again get the group 0 1 2 3 4 5 6 7. So here we can conclude that the union of all the coset of a subgroup will give us the group. Next is Lagrange theorem. The Lagrange theorem says that the order of each subgroup H of a finite group G is divisor of the order of the group. What is order of a group? Order of a group are the number of elements present in that particular group. Order of a subgroup is the number of elements present in the set of that particular subgroup. So here, this is the Lagrange theorem states that the order of a subgroup of a group will always be a divisor of the order of that particular group. Here I will prove this particular theorem. Let M be the order of group. Or we can say that M is equal to O of group and N is equal to O of H. And as we have previously concluded that if we take the union of cosets of a particular subgroup, we will get a group. So I can write this statement. We will get a group if we take coset of, this will be a coset of H, if we take union of cosets of H. So this is the theorem. If we take union of all cosets will give us group. This we have seen from the previous 3 examples. So this is this. So if we take order on both sides, order of G will give you a particular element, and these are all disjoint set. We can write that this as order of AKH. So order will give the number of element in this particular coset, and we know that the number of element in the coset are same as number of element in that particular subgroup. And here these are the coset of same subgroup. So these all values will be same. For example, if the number of element in the subgroup are, here we have already taken the number of element in subgroup are n, and these are the k values. So we can write this as k into n. These are k values, and here the number of element in coset will always be equal to number of element in that particular subgroup. So we can write this as this. Order of group is taken as m. So here k is equal to m divided by n. So we can say that the order of subgroup, which is n, is always a divisor of order of the group, which is m. So this is the Lagrange theorem. This is the reference textbook of discrete mathematics. Thank you for patience listening. Thank you so much.